you'll be able to find your minimum value of your inductor, which is L min will be equals to RT over 2 multiplied by 1 minus T to the power of 2 multiplied by your duty cycle. And then in order for you to make sure that your converter is always operated in continuous conduction mode, CCM, you need to make sure your value of inductor L must be greater than L min. So what is the percentage of what we call in selecting the value of IL? In selecting the value of L to make sure it's greater than L min. So we have this consideration whereby your minimum value of your L must be at least 25% more than your L min. So which is 1.25 you multiply by your L min over here. Okay, these are the waveform of the boost converter. We have the voltage as well as the current. So remember, for all type of DC to DC converter, the shape of the waveform will be the same. The only difference is the magnitude of your voltage and current for different type of DC to DC converter. Okay. All right. So finally, which is we come up in order to finish the analysis, we need to find the value for the capacitor. Okay, so the value of the capacitor, firstly you need to remember what is the function of having a capacitor in the circuit is that we want to get rid of the ripple, which is we want to produce a smooth DC output. Okay, we want to produce smooth DC output voltage, yeah. Alright, so that is the function of capacitor. It's nothing to do in setting the boundary whether the converter will be operated in CCM or in DCM. Alright, it's the only function is you want to reduce the ripple so that you be able to produce a smooth DC output voltage. Okay, so still we are using the charge equation. So from this charge equation, so we'll be able to get the equation for the capacitor, which is capacitor C will be equals to D over R multiplied by this is your percentage of your output voltage ripple. But remember, once you need to substitute in this equation in finding or finding the value of your capacitor, you need to change from percentage to numerical number, yeah. All right, and then this F here is your switching frequency. Okay, right, so now we proceed to the next one, which is in this example over here. Okay, you need to design a boost converter that deliver 80 volt of output voltage. So this is our V0 output voltage at 4 amp is your output current, and your Vs over here is your 45 volt. Alright, and then the output voltage ripple, which is delta V0 over V0 is given 1%, and your switching frequency is 20 kilohertz. So you need to design for continuous inductor current. Okay, so once it mentioned here continuous inductor current, okay, you need to make sure, you need to prove that whether is it the inductor current is continuous or not. So by means of that, you need to find what is your average inductor current, and then you need to make sure that your minimum and your maximum inductor current both are positive value. All right. Okay, so let us try this example number 1. Okay, I will guide you the step by step, and for the next example maybe you can give a try and then we can discuss during the Q&A session later. Okay, so from the question, so first the first and foremost, you need to find what is your duty cycle. Obviously you need to find your duty cycle. Okay, so from the equation of both converter, your duty cycle will be equals to your V0 minus Vs over V0. Okay, so we substitute the value, which is 80 minus 45 over 80. So you will get your duty cycle is 0.4375. Alright, so then we proceed to the next one. Okay, based on whatever available information in the question, so you need to find all the necessary parameter. So from the equation, it gives you the output voltage and also your output current. So you can, based on your power equation, you can use the power equation in order to find the value of your resistor. Okay, so your power P0 will be equals to V0 I0 equals to V0 squared over R. Okay, so your P0, which is 80, you multiply by 4 so you will get 320 watt. Okay, so you get this information over here, and then you'll be able to find your R, which is 80 squared over 320, which is your output power. So you will get your value of your value of your resistor is 20 ohm. Okay, next step number 3. Then once you find the value of your R, you can find your average inductor current. Okay, so based on the given equation that we did just now, so IL will be equals to Vs over 1 minus t to the power of 2 multiplied by R. So you have all this value of the parameter, you can just substitute the value. So 45 over 1 minus 0.4375 to the power of 2, then you multiply by 20 ohm. So you get your average inductor current IL will be equals to 7.11 amp. Okay, give a try, make sure you'll be able to get the what we call the value same like mine, so or maybe different in case I calculate it wrongly. Okay, right, then next step, so you need to find your maximum and minimum inductor current. If you are referring to the equation of maximum and minimum inductor current, you can see that there is L there. So you need to find the value of L first, then you be able to find the value of your maximum and minimum inductor current. So there are, in order to find the value of L, there are two ways. Remember the one that what we did in buck converter. There are two consideration or two criteria that you can use. One is that your L, you can use your L is 25% greater than L min. Okay, two criteria that you can use. Okay, L is 25% greater than L min. Okay, which is, if let's say that we make it a 1-to-1 ratio, so L equals to L min. Okay, so 1-to-1, so 1-to-1. So let's say in percentage, 100% L, 100% L min. So 25% greater, which is 100 plus 25%, yeah, greater than L min, so you will get 125% of L min, right, which is L will be equals to 1.25 multiplied by your L min. So from the equation of boost converter, L min will be equals to RT over 2 1 minus d squared multiplied by d. So you substitute all the value, so 20 2 multiplied by 20k, which is this one, 1 over f, 1 minus 0.4375 to the power of 2 multiplied by 0.4375, then you'll be able to get your L min will be equals to 69.21 microhenry. This is the value of L min. If you are using the value of your L min in order to proceed with the next what we call value of IL max and IL min, obviously you will get 0 for your IL min. So this, once you get 0, so it will indicates that your computer is operating in boundary condition, which is it will lead you to DCM. Okay, so you need to make sure your L must be at least 25% greater than L min, which is 1.25 multiplied by L min. So 1.25 multiplied by 69.21 micro. So you will get 86.52 microhenry. Okay, use this L and substitute in order to find the value of your minimum and maximum inductor current. Right. Okay. So step number 5. Okay, from the equation of IL max, which is IL plus delta IL over 2. So substitute the value, then you'll be able to get the value will be 12.8 ampere. And then for your IL min, which is your IL minus delta IL over 2, you'll be able to get 1.422 ampere. Alright. Okay, now lastly, the value of your capacitor. Okay, use the equation D over R, output voltage ripple, multiplied by your switching frequency. You substitute all the value of C. You'll be able to get your C will be 109.38 microfarad. So this is the value of your capacitor. Okay, this is when we are using the criteria of L equals to 25% greater than L min. So if let's say you are using the other criteria, which is involving the delta IL equation. So delta IL is 40% of your average inductor current. So you can use that as well, and in order to get the value of your inductor. Okay, if you are using that criteria, obviously you will get different value of L and different value of C, as well as different value of IL max and IL min. But that is not wrong, it's still correct, no problem. You can use either one of the criteria. Okay, right. So okay, give a try on this example number 2 over here. Okay, so that we can discuss it during the Q&A session later. Alright, so in this example, giving the input voltage of 5 volt and output power of, this is the output power, P naught will be equals to 25 watt. Okay, and your output voltage is 15. Okay, this is your Vs. Alright, and then it mentioned here your minimum inductor current is no less than 50% of average inductor current, which is this one. Your IL min is 50% of average inductor current. So you need to find your average inductor current. Half of your average inductor current is your IL min. Okay, minimum inductor current. You cannot use this what we call the assumption that the criteria that we made just now, which is the L is 1.25 L min here. You cannot use this equation. You need to, in order to fulfill the requirement that being specified in the question, which is this one over here. Alright, so you cannot use the IL mean equation, you cannot use that. Okay, this is the what we call the answer for example number 2 for your reference. So give a try. So in the next session, we will discuss on how to solve this example number 2 here. Alright. Okay, now we proceed to the next section, which is on the discontinuous conduction mode, which is the other operating mode for boost converter. Okay, for DCM, the assumption that we need to make is that we need to assume that your inductor voltage is 0, which is your VL will be equals to 0. Alright, and then we assume that the average current in the diode is the same as in the load current, which is your ID will be equals to I0. Alright, so the operation for DCM will be divided into 3 parts basically. The first part, which is the first mode, is when your switch is on and your diode become reverse bias. The second mode of operation is when your diode become forward bias and your switch is off. And the third operating mode is when both switch and diode they are off. So whereby in this mode the current as well as the voltage they will be 0. Alright. Okay. Alright, so these are the typical waveform in DCM. So the first one is the average inductor current IL, and then the second waveform is VL, voltage across your inductor, and the third one is your diode current. So if let's say that for example in the lab, the OEL lab for DC to DC converter, you need to produce a waveform. So make sure you be able to produce with this kind of waveform with similar shapes. Okay, the value or the level of the magnitude might be different because it depends on your value of the parameter that being using, but the shape should be almost the same as the one that being presented in the lecture. Alright, okay. So as you can see from the inductor current over here, you can see that the waveform start at 0, which is by mean of this is that your IL minimum inductor current will be equals to 0, and then it will rise up to the maximum point here, IL max. Okay, and then it will go down. Okay, this is the period when your switch is off, your diode become reverse bias, and this is the period when both off, your switch and also your diode both are reverse bias, both are off. Okay, so we know that if let's say that we define the inductor current in terms of variation of inductor current, which is delta IL over here, so your delta IL will be equals to IL max minus IL min. So in this case, in DCM, your IL min equals to 0. So you know that your delta IL will be equals to your IL max over here. So we have one clue in order to help us in finding the analysis of voltage and current in DCM. Okay, and then we have the second clue is that we assume that the diode current will be equals to your output current. Okay. So how to find this relationship of input voltage Vs, output voltage V0. The duty cycle, bear in mind we have two duty cycle, which is D referring to the first operating mode, and D1 is referring to the second operating mode. Okay, so in order to find this relationship, so we need to find the delta IL when switch is on. Okay, and delta IL when switch is off. Okay, for delta IL when switch is on, as the equation will be similar as the one in CCM, which is Vs over L multiplied by dt. Okay, for the delta IL equation when your switch is off, this is when your diode become forward bias, will be equals to Vs minus dt over L multiplied by the delta T here will be equals to D1T. Okay, remember in CCM it will be the delta T will be 1 minus T times T. But in DCM it will not be the same. It will be D1T. So our main task is that we need to find out what is equation that relate in order to find the value of D1 and as well as in order to find our output voltage V0. Okay, so from these two equations over here, we equate these two equations together by using KCL, and then we rearrange and cancel the similar terms, and finally we'll be able to get the output voltage equation in DCM. Okay, which is V0 will be equals to Vs multiplied by D plus D1 over D1. So this is the equation that you need to use whenever your converter is operated in DCM. Okay, so now we need to find the equation that relate with D1 to find duty cycle 1. So based on the previous slide, the waveform, we have some information, which is we know that your duty cycle, the diode current will be equals to your output current. So we need to find the average. So we need to do the integration, which is we need to find the area under the curve. So if we integrate with respect to one switching time, so 1 over T, okay, which is integrate from 0 to T. Alright, so this is half multiplied by IL max multiplied by D1T. So if you refer back to this one here, yeah, okay, we need to find this area under this curve over here. So based on the area formula for triangle is half multiplied by your height. Height in this case is IL max. Okay, so IL max, and the width here will be D1T. See this one here. Alright, so then you'll be able to relate between your diode current and your output current. So your diode current will be equals to your output current, which is your output current, if let's say that we define in terms of voltage and resistor, will be V0 over R. So your IL max, based on the previous waveform, we know that equals to delta IL because your IL min is 0. So since you have the equation of delta IL, so you can use either one here of this equation over here, yeah, either this one or this one. Okay, choose either one, the one that has the least unknown parameter. Alright, so in this case I choose the first one, which is Vs multiplied by dt over L. Okay, and then we substitute inside this equation over here, which is we substitute inside the IL max term. So your diode current now will become half multiplied by Vs dt over L multiplied by D1 equals to V0 over R. And then we rearrange, we take out the D1. Okay, finally we'll be able to get this equation over here, which is D1 will be equals to V0 multiplied by 2L over Vs multiplied by R multiplied by dt. Okay, right, so that is from the one that I wrote in the previous slide. So this is basically all the what we call the equation that relates to DCM. Alright, okay, and now if let's say that you don't have enough information to find the output voltage in DCM, there are another way for you to solve in finding the output voltage, which is by using this equation over here. So based on the equation here, and then you substitute D1 with the previous equation that we did just now. Okay, and then you rearrange the equation, and then you'll be able to solve your output voltage. If let's say that you need to find your output voltage, yeah, okay, will be equals to this equation over here. Okay, right, so if let's say that you need to solve the output voltage, so you just bring Vs to the side. Okay, it make it from the denominator become numerator. Okay, so you can see that from this boost converter in DCM, okay, previously in CCM, in order to find your output current, it only based on the value of your input voltage, which is Vs, and your duty cycle. But when you need to find the output voltage in DCM, okay, it's not only depending on the duty cycle and Vs, it also depends on the value of your inductor, the value of your switching frequency T here, and as well as the value of your R. Okay, so if let's say that any of these variables varied, for sure your output voltage will vary as well. Okay, alright, so this is the example number 3. Okay, in this example is actually referring to the boost converter in DCM mode. Okay, so giving this set of parameter over here, okay, you need to verify that the inductor current is discontinuous. So you need to prove that whether the inductor current is discontinuous by means of inductor current. Okay, so you need to show that your IL min must be 0 or less than 0. Okay, so this will prove that your inductor current is discontinuous. Okay, there is also another way to define the mode of operation for a converter, which is by using L min. Okay, so you need to find the L min. So and then compare with the given L in the question. So if let's say that your L, the given L is less than your L min, okay, it also indicates that your converter will also operate in DCM. If let's say that your L is more than L min, then it will be in CCM. Okay, right. Let's go to the solution for this example over here. Alright, so like I mentioned previously, we have two ways to determine a DCM mode for a converter, which is by using L min and as well as IL min equation. So if let's say that we start with using the L min equation, so we from this equation over here, we substitute all the value, then we get the L min, the value of L min, which is the minimum value of inductor, is 120 microhenry. Okay, from the question, the L that been given is 100 microhenry. So obviously, your L min is greater than your given L. So it will indicate that your converter is operated in DCM mode. Alright, so if let's say that we are using the IL min equation, okay, to indicate whether the inductor current is discontinuous, so you need to check, make sure that your IL min is either 0 or less than 0. Okay, in let's say that in calculation there is no problem, you can get negative current, but in practical, okay, it's no way you can get negative current because we have the diode inside the circuit, right? So this diode will block the current from going to the negative region. So the least amount of current will be at 0. Alright, so using this IL min equation here, we substitute all the value and then we solve the equation. So we get the IL min equation equals to minus or negative 0.5 M. Okay, so since it is what we call less than 0, so it will indicate that your the inductor current is discontinuous. Alright, okay, then so you're the answer for part A. Then for part B, you need to find the new voltage. Since your converter is now operating in DCM, okay, obviously it will not be, you can't use the output voltage that been given in the question. You need to find the new one. So from the equation, okay, you can refer to the previous slide to find the equation of V0 here. Okay, so I use this equation here and I substitute all the values. Okay, and then I'll be able to get the output voltage we know will be equals to 53.59 volt. Okay, try to do the calculation just in case that I calculate it wrongly, so that you can correct me whenever we have the next session, the live session. Yeah. Alright, okay, and then finally we need to find the IL max. Okay, we use VSTT over L. Okay, and then you substitute all the value. Okay, and your maximum inductor current that we should get is 6 ampere. Alright, so I hope all of you able to try and to work out on the what we call on the answer that been given here. Okay. Right, so I think this is the finally, yeah, the last slide for boost converter. Okay, so as a conclusion, a boost converter can step up the output voltage without the use of transformer. Okay, okay, due to a single use of switch. Okay, so it will has minimal losses, so it will produce a high efficiency of the converter. Alright, okay, what else? Okay, and then it mentioned here the output voltage is very sensitive to the changes in the duty cycle. Obviously, from the equation we know that your output voltage is only depending on the duty cycle and Vs, so any variation of these two parameters will affect the output voltage. Okay, here, right, okay, the average output current is less than average inductor current by a factor of 1 minus d. Alright, okay, this is what we call we need to calculate refer back to the previous slide. Okay, alright, and then the use of a large filter capacitor, okay, and also large value of inductor. Okay, this is comparison between the buck and boost, which is if let's say that you have the similar parameter, similar value of Vs, duty cycle and so on. Okay, and using the equation to find the value of inductor and capacitor, you can see that in boost converter the value for the C and L is bigger than in boost, is bigger than the C and L in buck converter with the same parameter. Okay, right, okay, so remember, okay, for the converter it has two operating mode, which is CCM and DCM. So bear in mind what are the equation that relate with CCM mode and what are the equation that relate with DCM mode, and please do familiar with the waveform, the shape of waveform in CCM as well as in DCM. Alright, because it will help you in doing your OEL DC to DC converter as well as in your online test later. Alright, so till then, okay, take care. I will we will stop for now, and hopefully I will be able to do what we call a recorded video on the next type of DC to DC converter, which is buck boost converter. Okay, stay safe.